So, as I mentioned, we're here to talk about missing data. This is part one of a two-part set. Today, we will be talking about an overview of missing data. And then I always like to start these types of presentations by talking about prevention, because this is literally an area where an ounce of prevention truly is worth a pound of cure. I mean, there are all kinds of fancy statistical things you can try to do to close the barn door after most of the horses have escaped, but if you can do that ahead of time, that's really the best medicine. Then, because missing data, even with your best prevention efforts, are inevitable, we'll talk about missing data mechanisms, which is how the data came to be missing in the first place. And this is important not just from a pedagogical or theoretical standpoint, although that's kind of interesting, but it's also going to influence how you treat the missing data in your statistical analysis. Then we'll talk about traditional, what I would call 20th century, early, mid, mostly late 20th century methods of handling missing data. These are ad hoc approaches that are the most commonly available in statistical software packages even today. Then we'll talk about the maximum likelihood method of handling missing data, which is an approach that, although conceptually it was developed in the 1950s, computationally it really was not feasible to use until the mid-1990s. Then we'll show you three examples. One is a linear regression via maximum likelihood estimation. Another is a logistic regression via ML. And then we'll talk about a longitudinal analysis via maximum likelihood estimation. And for those of you who've seen previous iterations of this talk, this longitudinal analysis is new for this particular presentation. Then we'll conclude and go through acknowledgments. And as I did mention, this is the first in a two-part set. So we're going to concentrate on maximum likelihood estimation today, and then in 2 weeks, same time, same channel, same location, we'll talk about multiple imputation, which is another method you may have heard about that's being used increasingly to deal with missing data. So, to start out, missing data are ubiquitous in applied quantitative studies. It can arise from situations where you have a don't know, a don't remember, or a refused response on a cross-sectional survey. And it's particularly prevalent for self-administered paper surveys. Now, I know that with the rise of personal electronic devices like iPhones and iPads and things like that, smaller and smaller computing devices, paper surveys are falling more and more out of favor and are being replaced by electronic data collection. But even if you have electronic data collection, there can still be instances where you'll have missing data. Again, you might have don't know, don't remember, and refused responses that are not missing when you treat them as univariate quantities in a frequency analysis, but when you go to sum them up or create some kind of scoring, those might convert over to missing. Even in electronic survey instruments, it's been my experience that there can be sometimes a disturbingly large number of errors. You need to check when you create a computer-assisted interviewing instrument. And here we have ACASI, which stands for Audio Computer-Assisted Self-Interview. So that's with low literacy populations, you can have a headset that somebody wears that will read a question to them, and then they can respond. But it's absolutely critical that you test your ACASI instruments repeatedly to make sure that all the skip patterns are working and that you don't have any potential omissions that could lead to missing data. And of course, if you're doing longitudinal studies, and I know a lot of folks here at the Osher Center are doing a lot of trials, longitudinal evaluations of interventions, you're inevitably going to have some loss to follow-up. Some participants will drop out and never return. Other participants may drop out of a particular session, and then they come back for subsequent sessions. Yeah.
A question, because I'm still struggling with you're putting the don't know, don't remember, refused responses in a certain sense in the same general category as what I would usually worry about with missing data, which is that the skip pattern is wrong, or people didn't fill out the questionnaire. Can you
Right.
say a little bit more about that? Because to me, that's almost an issue of study design. If you don't want a don't know kind of response, then you kind of have, one thing you really have to think about is forcing a response if at all possible. But if people really don't know, that's different to me than someone didn't fill out a questionnaire.
Right, absolutely. And I think your point is very well taken. You want to address these issues at the design phase as much as possible. And there is a sense in which coding somebody's response, don't know, don't remember, or refused, is a legitimate response. And certainly you could treat those as non-missing, but then the question becomes, if they're a response to some kind of larger instrument that has maybe like 10 or 15 or 20 items, what do you do when somebody has a don't know or don't remember and you're wanting to create some kind of summated scale score? It's definitely problematic. So you could do more advanced things like two-part modeling, where you create a class of people who don't know or don't remember or refused. Typically the numbers of people who endorse those categories may be small, especially if you've designed your questions well. So two-part modeling strategy is obviously going to need enough people in those categories for the estimation to work correctly. So anyway, it gets complicated pretty quickly. But yeah, I mean, absolutely, you want to be very careful in the way you design the instruments up front.
Mm-hmm. And if it's a categorical variable, you can have another category. But if it's a continuous variable, it really messes you up, right?
All right. So, the scary box. This is a paper survey that was administered to young adults here in the Bay Area in the last couple of years. And we did do some electronic data collection and collection by phone, but there was also some mail surveys that were sent out. And the post office managed to send a number of them back in this condition. And we were able to recover certain parts of some of them, but unfortunately some of them were lost. So this is just an illustration. I like to have a slide in my PowerPoint that's not equations and not just text. But anyway, the investigator was very generous to let me share this on my slides, and just a kind of a recent object lesson that indeed missing data can happen even in a well-designed study, which this particular one was. I mean, this was not her fault at all. So let's talk a little bit about prevention. So for computer-assisted interviewing, ACASI, that's a self-interviewing. CAPI, that's a computer-assisted personal interview where you might go up to somebody and you have the data collection device and you ask them questions, and then you or your research assistant enters it into the device. Those electronic data collection mechanisms can be very helpful in the sense that they can catch logical inconsistencies, like if you ask someone, did you smoke any cigarettes in the last 30 days? And they say no, and then the next question is, how many did you smoke? The electronic skip pattern can be programmed so that if they say no, they can skip over that question. The electronic data capture programs can also catch inconsistencies. So if someone later in their survey says, well, I smoked 3 cigarettes in the last month, and then earlier on they said they had not smoked anything in the last 30 days, you can have programming in there that catches that inconsistency and flags it in real time. And so that can help prevent inconsistencies and missing data. Now, for longitudinal studies, rigorous retention protocols for participant tracking is really important. So I've learned from my colleagues, for instance, that regular contact with your research participants, even if it's not for a measurement occasion, is really, really important to maintain the participants feeling connected with the study. And so then that enhances, when there is a bona fide measurement, that they will come in, or they will take your electronic survey or participate, continue to participate. And then a couple of faculty and a statistician down at CAPS, Diane Benson, Bill Woods, and Lance Pollock, are working with a method called flexible interviewing. So if in a survey instrument, if you ask someone, is your favorite color blue or red, That's not very cognitively demanding or very difficult. But if you begin to ask people questions about things that are very difficult or amorphous to define, like, did you feel pain in the last day? And then people say, well, does the day include the night? Or does it include when I was just awake? Or did you have sex with that intern? Well, it depends on what your definition of is, right? Or your definition of sex, or your definition of intern. So, because we do a lot of sexual behavior and substance use research at CAPS, there's been a lot of discussion about how can we get at a better shared understanding between the research participant and the researcher, because we go in and we talk amongst ourselves and we say, well, when we talk about sex, or we talk about drug use, or we talk about pain or symptoms, we can all, as researchers, sit around the table and come to a clear consensus most of the time fairly quickly about what those things mean or what we want from the participants. But the participants may have very different ideas about what those things mean. In a standard interviewing paradigm, if a participant asks the interviewer, what do you mean by sex? Or what do you mean by symptoms? Or what do you mean by pain? The interviewer can only say, it's whatever it means to you. I can't tell you. And the reason for that paradigm is because that is intended to reduce bias, right? You don't want your interviewer giving anything but the same treatment to all the research participants. However, an unintended consequence of that is that it makes the interview for participants extremely frustrating if they're asking questions, because they're there and they're like, I want to help the researcher, I want to give the best answer I can, and this researcher is really just not giving me anything back, and that's unbelievably frustrating. And it can be very frustrating for the interviewer too, who might want to help but feels like they're straitjacketed and they can't. So what a flexible interviewing method does is it enables the interviewer and the participant to engage in a dialogue to try to arrive at a shared understanding of what it is that's being asked. And there's some researchers at Michigan, Fred Conrad and some others, who have studied this method and showed that if you do this with very difficult to grasp topics, not only is the interview experience better for the research participant, but you get better data. And what Diana and Bill and Lance have done is take this into the realm of sexual behavior and AIDS research, and they've been able to reduce don't knows and missing data due to don't knows up to, I think it's like 70 to 80%. And now, it sounds good in principle. The big limitation with it from a pragmatic standpoint is it's very time consuming. So you would not want your whole survey instrument to be flexible interviewing. You would only want your most critical questions that are the most amorphous and difficult to grasp to be in that paradigm, because it can be very intensive and you won't get through very many questions. Another thing that's been suggested in the literature, which is really interesting, is if you're doing a longitudinal study, Leon et al. Published a paper in Clinical Trials where they said, ask the participants on a 1 to 9 scale, do you anticipate a problem in coming back for your subsequent visit? And what they found is that then you could use the respondent score on that as information in your subsequent data analysis to help you meet the assumptions underlying the maximum likelihood and multiple imputation missing data methods that we'll be talking about. Now, when I looked at the article, I thought, well, that's cool, but that's, again, closing the barn door after the horse is already out. If you have a real-time survey, why couldn't you ask this question and then have it flag something for the interviewer that says, hey, this person is anticipating they're not going to be able to come back. Let's troubleshoot with them now while they're here ways that we can ensure that maybe they'll come back. So maybe they'll say, well, I don't have childcare on the next day that you scheduled me to come. Well, can we schedule you on a different day? Or, or I don't like this survey. Well, is there anything, we can do to help with that, help you maybe dislike it less, or, understand this was a big baseline survey, and if you felt like this one was too long, rest assured the next one's only like half as long. Those kinds of things to help people feel more comfortable about the idea of returning. But even if they don't, you have the data that can help you reduce whatever remaining bias there is when they do fail to return. All right, so let's talk a little bit about missing data. Let's say you have some missing data and what we want to know is how did the data come to be missing in the first place? And a really smart guy named Don Rubin in the mid-1970s published an influential paper in Biometrica where he defined 3 different types of missing data. And these are named very confusingly missing completely at random, abbreviated MCAR, missing at random, which is abbreviated MAR, and then not missing at random, NMAR, also sometimes abbreviated as missing not at random, or MNR. And there's some really nice articles in the literature, in the social and behavioral sciences literature, that spell this out. One is by Joe Schaefer and John Graham in Psychological Methods, and that's kind of like the long, full treatment. And then Graham in 2009 wrote an annual review of psych chapter that's really, really excellent. For anyone who's a social and behavioral scientist, it's extremely clearly written and really lays out the missingness mechanisms, and then also the remedies that are used, including maximum likelihood and multiple imputation. So I would encourage you all to look at that Graham 2009 article. That's one of my favorites. Bless you. Okay, so we'll take an example from Schaefer and Graham's article. And one way to think about MAR, MCAR, and NMAR is to envision a scenario where you have some observed data in a variable X and missing data in a variable Y. And if you're willing to assume independence of observations, which is an ordinary assumption that we make in many statistical analyses, then missing completely at random indicates that the probability of Y being missing for a particular participant does not depend on her values of either X or Y. Missing at random indicates the probability of Y being missing for the participant may depend on her X values, but not her Y values. So this is sometimes referred to as conditionally missing at random, because the missingness on Y is conditional on something else for which you have observed data. And one of the things that Schaefer and Graham point out towards the end of this paper is that in social and behavioral research, we often have information in variables like X that can help us figure out if somebody is missing on Y or not, right? In social and behavioral research, often many things are related to other things. So it's a little less maybe like a drug and device trial where if there's some adverse reaction that's due to a drug and it's hard to correlate that reaction to anything else that we may have measured, although again, this is where your subject area knowledge would hopefully help you figure that out ahead of time at the study design stage and incorporate things that can help you account for that missingness. In social and behavioral research, we often have that kind of thing built in by measuring things like education, race, ethnicity, income, geographic location, and the list goes on and on. In longitudinal studies, a particularly powerful measure is something that was filled out at a previous measurement point, the same variable. So, if you ask somebody, what number of sex partners you've had or what level of pain you've experienced in the past 30 days, and maybe you have a baseline measurement for them, but they skip a follow-up, it's often the case that somebody who had a lot of pain before may have pain now, or somebody who had a lot of sex before is going to potentially have a lot of sex now. So we can gain information, and that can help us meet the MAR assumption. Now, NMAR is the worst possible situation to be in, because in NMAR, the probability of Y being missing depends on the participant's actual Y values, and not necessarily X. So this is a situation where the very thing that you're measuring is missing, and that's the thing that's driving whether somebody is missing or not. So for instance, if a doctor says, well, I want to measure Tor's weight, but Tor doesn't want to come in because he had kind of a very excessive holiday celebration, and he's feeling heavier than usual, and he's embarrassed to come in and get weighed, and weight is the thing that's being measured, and the doctor has no other information about Tor other than the weight measurement. That's going to be an NMAR missingness situation, because it's my weight that's preventing the doctor from getting data on my weight. Now, there are formal probability-based definitions for these terms, but it's early on a Friday morning. We've got a lot to get through, and I wanted to have mercy on you guys, so we've relegated those to an appendix. But they are there for those who are curious. All right, let's think about an actual concrete example, because all that was kind of at the 30,000-foot level. Let's bring it down now. And Schaefer and Graham, again, we'll turn to them. They give an example where systolic blood pressure is measured in February as well as January. And if you have SBP data that are missing in February, and that's just random, right? Let's say your measurement instrument for blood pressure went on the blink and you lost some data due to that measurement instrument having a problem in February. Maybe the batteries didn't get changed or something like that. Now that missingness and the SBP score that would have been observed had we had an accurate measurement instrument, had working measurement instrument, that's unrelated to what their SBP score would have been in February, and it's also unrelated to the measurement that had been taken in January. Now, let's think about missing at random. Data are missing in February because the January measurement did not exceed 140. So now we have cases, we're going to assume that cases are missing randomly within two groups: January systolic blood pressure greater than 140 and systolic blood pressure less than or equal to 140. So we're able to utilize information from January to get a sense of what's missing in February. Now, not missing at random. The worst case, data are missing in February because the February systolic blood pressure measurement did not exceed 140. Let's say, for instance, someone said, well, I took it, but I'm not going to record it if it's less than or equal to 140. Maybe I think this is a really great intervention for participants, and they're only supposed to get the intervention if they have high blood pressure, but I'm a cowboy research assistant, and I think that everyone should get this intervention. And you guys are laughing, but this kind of thing has happened sometimes where research assistants have tried to give people in the control group some intervention dosing. So in this situation, the case data would not missing at random because it's the February measurement that's really affecting whether the data were observed. Okay, so you have missing data. Now the question becomes, how do we deal with it? And there are a number of approaches that were suggested back in the last century for handling missing data. We group these under what we call ad hoc approaches. You have Listwise deletion, which is also known as complete case analysis. You have Pairwise deletion, which is also known as available case analysis. Then you have dummy variable or indicator variable adjustment, which is something that Cohen and Cohen came up with. Then there's single imputation with the variable or participant means, and we would also add to that things like medians or modes. It's the same idea. Then there's also using multiple regression to try and plug in missing values. So generating a plug-in value based upon multiple other predictors for which you have observed data in the data set. And there's something called hot deck. And we're going to show separate slides for each of these and define what they are. So listwise deletion of missing data. This is the approach that's used by most general purpose statistical programs. And what they do is they look at the data record and they say, well, if I'm using if I'm going to analyze a multivariable regression model, logistic regression, linear regression, Poisson regression, whatever, I'm going to delete the whole case from the analysis if one or more variables values are missing, and I'm only going to use cases with complete data in the analysis. So if you're in a situation where you've got like a 10 predictor model and one predictor is missing data, that case is gone. And so you can see that you might have a little missing data here, a little missing data there, And like that senator said, you have a few $1 million here, a few $1 million there. After a while, it begins to be real money. Well, it's the same kind of idea here with missing data. A little missingness here, a little missingness there, and with listwise deletion, all of a sudden you're down from 1,000 cases to 100 cases. The other thing, so that's a pragmatic issue. So statistically, the consequences of listwise deletion are summarized in this table below, and it depends on whether you have missing completely at random data or not. If you have missing completely at random data, one way to think of that data for which you have complete cases, those data are basically a random subset of the whole population of cases, and so your parameter estimates will be unbiased. So your regression coefficients will be okay. But if you lose a lot of data, your standard errors will get bigger because n is used in the standard error formulas. And so the result of that is that you will lose power for hypothesis testing. And we don't like that because we want maximum power to test our hypotheses so that we can draw good conclusions about our data and get published and get our grants and continue to do good work. So that's the consequences in the situation where you have missing completely at random. If you're in a missing at random or not missing at random situation, the consequences are even worse because the parameter estimates will be biased. So you can get incorrect odds ratios, incorrect linear regression coefficients. So we definitely don't like that. Pairwise deletion of missing data. Well, what about the idea of using all pairs of available cases for computation of any sample moment? A sample moment is a thing like a mean, a standard deviation, a correlation, a covariance. So what pairwise does is it says, well, for means and variances, where we're talking about one variable, we're just going to use all the available data to calculate that statistic. Then for a covariance or correlation where you have pairs of data, you just use all the available data on pairs. So for instance, if you had variables A, B, and C, and variables A and B had 30 cases in common, your A-B correlation would be based on an n of 30. But if B and C had 50 cases in common, your B-C correlation would be based on a n of 50. Now, a consequence of this is that you can get what are called non-positive definite variance-covariance matrices, because when you calculate up a correlation or covariance matrix, you are using different sets of cases to build those correlations and covariances, and that can sometimes lead to inconsistencies in the correlation or covariance matrix. Now, the other thing I've seen it a little bit, but it may not be hugely common, but you do have a dilemma anytime you try to use pairwise missing data handling when you're doing regression modeling where you have multiple predictors, because the n now varies across different pairs of variables. If your n's vary from like 30 to 32, maybe that's not such a big deal. But what if your n's vary from 30 to 50 or 30 to 60 or 300 to 1,000? Well, what n do you use for the analysis? You're kind of stuck. And then, like I said before, this pairwise deletion, like listwise, it can lead to biased standard errors when you're dealing with a situation where you have missing at random data. So, Cohen and Cohen, two extremely smart people, came up with, in the early 80s, the following approach. When X has missing values, you create a dummy or indicator variable indicating whether the case is complete or not for that variable. When X is missing, you fill in a constant, C. Then you regress your outcome on the original variable X, and then this dummy variable D, and then any other non-missing predictors you might have. But in 1996, Jones came along and spoiled the party and said, no way, this does not work. It's going to give you biased coefficient estimates. And that was published in the Journal of the American Statistical Association. So what about single imputation? This one's really attractive, right? I mean, the idea here is you might take a mean on the variable, so go down the column for a given variable, calculate up the mean or the median, and stick that back in the data set for any records that have missing values. Or sometimes if you're dealing with a multi-item survey instrument, I've seen people do a conceptually similar thing, but do it based on the row of the data, right? Maybe you have 10 items and one of them's missing, so you take the mean on the other 9 and you stick that mean back in there, and then you ostensibly have complete data. Now, a slightly more sophisticated way, a step up from that, is regression imputation, where you say, well, okay, I've got a missing value on item 8, and I'm going to use items 1 through 7 and 9 and 10 to predict what 8 should have been. So the thing that's attractive about that is you're using multiple pieces of information now to estimate a conditional mean, which you then plug in. Now, HotDec is something that was used at the US Census for a number of years, and the idea behind HotDec is that you pick a donor case at random from homogeneous strata of observed data to provide cases with unobserved values. So, for instance, if you want to try to impute the missing number of publications for a postdoc at the Osher Center, what you would do is you would identify a group of postdocs who are at the Osher Center who have complete data on the number of publications, and then at random you would pull a value from that group of postdocs and plug it in for your missing postdoc. Now, unfortunately, all of these ad hoc approaches can lead to biased parameter estimates, which include means and regression coefficients, and also variance and standard error estimates that are biased downwards. So if you think about it, like when you do mean substitution, you're plugging in the same value over and over again for missing data. If we had observed those cases, those people probably would not have all had the same value. So what we're doing is we're artificially shrinking the variance of those variables, and that can lead to bias. Now, it turns out this guy named Roth in 1994 published a paper that said, you know, it turns out that if you have very small amounts of missing data, say 5% or less, it doesn't really matter what you do, Listwise, Pairwise, mean substitution, you're going to get pretty similar answers. And this is really good news, right? Because every so often I'll get an email or a call from someone who says, I've got 1,500 cases and I'm missing like 3 people on race. Should I use like really fancy multiple imputation and like spend days doing all these diagnostics and all this crazy stuff? And I'm really happy to be able to tell them, no, just use listwise deletion. Just let the software drop those 3 cases, and it's cool because it's a very tiny amount of missingness. But when you start getting above 5%, then things begin to shift a little bit, and it's a really good idea to look at other potential methods. Okay, so what do we do if we have MAR missingness? And I'll just say that the literature talks a lot about MCAR, missing completely at random, as being this kind of unrealistically strict, rigid assumption that's often not met in practice. But MAR is much more a much more relaxed assumption, because we often have, like I was saying earlier, additional information we can bring in to help inform the analysis. So there's been interest in the statistical literature on methods that will work for MAR missingness. And Joe Ibrahim in 2005, and Jazza again, reviewed 4 general approaches for handling MAR missingness and found all to perform about equally well. The first one is inverse probability of censoring weights. And for those of you who are interested in causal inference methods, that's the approach that people who do causal inference really like, because basically what it does is you build a statistical model to predict missingness. And you use multiple variables, kind of like the way, for those of you who are familiar with propensity score methods, it's a very similar logic, right? You basically generate a predictive model for propensity of missingness, and then you calculate an inverse probability weight of missingness, and you utilize that weight in your subsequent analysis to improve the accuracy of the estimates. IPCW is great. SAS, in its most recent release in Prot GEE, has implemented it so that you can specify a separate model line for the probability of missingness. I believe ProcG will only implement that if you have monotone missingness, which means, for instance, in a longitudinal study, people who drop out at time, let's say in a 3 time point design, they drop out at time 2, and then they're also gone at time 3. So you can't have people dropping out and then coming back in, at least the way this has been implemented in SAS. Now, I expect that eventually it'll be more common in general purpose software, and that restriction about monotone missingness will probably be relaxed. I've seen this used most frequently when you have like one key variable, like say a missing dependent variable, for instance, in a trial, where you might have baseline data, on everyone at all the other variables. And because the issue is, like, if you have a lot of variables with missingness, you have to create an inverse probability of censoring weight model for each one of them, and then you have to figure out how to join those weights together. And I think it's probably, I'm not sure, but I would guess probably like the product of the weights. So it's kind of an involved operation. The other thing that Ibrahim found was this method was a little less statistically efficient than the other 3 that are listed below it. But again, perfectly good method if you're dealing with weighted data, as in propensity score methodology, as in causal inference. It's kind of a natural extension of that too, so there's that appeal. Okay, that's IPCW. Fully Bayesian analysis. We could spend forever talking about Bayesian analysis, but the cool thing is, here at the Osher Center, you guys have an expert in Bayesian analysis. Mike, he studied it. He knows the history of it. But in the Bayesian framework, parameters are not considered to be fixed quantities. They are actually varying and are estimated. And so when you have missing data become additional quantities just to be estimated as part of the modeling process. So if you're willing to assume missingness at random, in the Bayesian framework, missing data just becomes part of the modeling process, and it's all very seamless. The challenges with Bayesian analysis are that for all but the simplest models, you need advanced simulation methods to generate the estimates for the model, and now there are software programs with modern computers being pretty fast now. You can simulate the Bayesian models and distributions, and there are, for instance, in SAS, several of the procedures now have built-in Bayes statements to make this process easier. There are also standalone procedures for writing your own Bayesian models, and there's even a freeware program called WinBugs that will allow you to do it in Windows, and will fit a tremendous variety of statistical models. So Bayesian analysis is certainly a very fine way to handle missing at random. It does require that you specify prior distributions, which are like your beliefs about what the distributions of those varying parameter estimates will look like. So there is an additional onus on the analyst and the researcher to do that. Some might view that as a disadvantage. Others might view that as an advantage because it does hold the researcher maybe to a higher standard of what their prior belief is about what's actually happening with the model and the data. The other thing is some people have argued, and Mike, you can correct me if I'm wrong about this, but that Bayesian modeling really represents more the way we actually think about statistics and data and hypotheses and statements and conclusions that we want to draw. So in the standard paradigm, which is what is called frequentist, you assume that you would run an experiment, say, a huge number of times, and there is a fixed value of the parameter in the population, whereas in Bayesian analysis, that parameter can vary.
I would say that's what the Bayesians would say.
Okay.
I don't happen to believe that Bayesian theory models thinking.
Okay, thank you. So that leads us to maximum likelihood estimation, which is sometimes called full information maximum likelihood, or FIML, and that's what we're going to talk about today. And then there's multiple imputation, sometimes abbreviated MI, and that's what we'll talk about next time. And Ibrahim showed that those two methods perform as well as IPCW or fully Bayesian. Now, one thing that's kind of cool here is that MCAR missingness, it turns out that MCAR missingness is really a specialized subset of MAR missingness. So if these methods will work for MAR, they'll also work for MCAR. And that's great because that covers 2 out of the 3 mechanisms that we discussed earlier. And if that weren't good enough, then it's also the case that some simulation studies have shown that methods that assume MAR missingness may outperform ad hoc approaches, leading to less biased parameter estimates even when the data are missing due to a not missing at random process. And I think that probably has to do with the fact that these MAR methods can bring in all the available information that you have in the data that you actually have observed. All right. So now Estie's going to take over and talk about maximum likelihood theory.
And I'm sorry, since it's a lot later than when we started, I can have some formulas, right? Anyway, but hopefully it won't be too much. So I'm going to talk about some of the theory behind maximum likelihood. In general, when there is no missing data, we use maximum likelihood to estimate parameters and standard errors. And the likelihood function is a function that expresses the probability of the observed data. It's the density if you have continuous variable. I won't tell you what that is. Given the parameters as a function of the unknown parameter values. So then you take this mathematical function and you find the maximum. That is the value of the parameter that will maximize the value of the function, of the likelihood function. So these estimates or estimators are called the maximum likelihood estimators, or MLEs. And here's a simple example. So L for likelihood of the parameter theta, assuming, as Tor said before, that our observations are independent, or cases, as Tor called them, and this is so we have 2 variables, an x and a y. The measurement of x on the I observation is xi, and on the measurement of y is yi, but we have pairs of values for each observation, the xi's and yi's. So the likelihood function is the product of the individual probabilities of the pair xi, yi, given the parameter theta. Now, this can be extended for more than 2 variables, and it can be extended for, the theta can actually be more than 1 parameter. It can be a vector of parameters. And here is where the independence assumption comes in, because if your observations are not independent, you couldn't write this as a product. Okay, so this is the joint probability of observing xy given the parameter theta for a sample of n independent observations. Okay, so the likelihood function is the product of the separate of individual contributions to the likelihood from each observation. And I already said that, so I probably don't need to repeat that. Now, under ordinary conditions, the ML estimates are consistent, which means they are approximately unbiased in large samples. And unbiased is what we want, because it means that the value that you get actually measures the parameter. It gets you as close as possible to it gets you the parameter you want to get. They are asymptotically efficient, which means among unbiased estimators, they have the smallest possible variance, which is nice to know, because when you have one sample, you don't know that you get the correct value, right? But if the variance is small, then you know that you're close to the correct value. Okay, and this is very important. They are asymptotically normal, which means in large samples, you can pretend like these estimators came from a normal distribution. And this is the case even when the original distribution of the XY pairs, it can be almost anything. Okay, but the distribution of the parameters is normal. So you can use the normal theory, the normal probability distribution to get all these p-values, confidence intervals, and things like that. Now, the maximum likelihood approach can be very easily extended to the missing at random situations. And what you do, you divide your data into two parts. The part that is not missing, and you have the product of the pxi, yi given the parameter theta. And we are assuming, it's just a matter of order, that the first m observations have all data, non-missing data. So you have the product of that. And then for the ones that are missing, you get the marginal. That is, you use the information that you have there as a contribution to the likelihood function. And what g of yi given theta is, as I said, is the summation of px yi over, for that particular xi, and that's, as I said, it's the marginal distribution. And so it is using two things here. The independence, which gives us the ability to create a product, and the fact that the values are distinct, or disjoints, which gives us so they are not overlapping, which gives us the possibility of adding things up without having to worry that we counted things more than once. Okay, so, and this likelihood may be maximized like any other likelihood function. Tor said that, so I'm not going to repeat it. It's also called direct ML. Okay, and the next one, I'm going to show a very simple example. It's a 2x2 table with missing data. So there is the relationship between sex or gender and voting behavior of people. And you have the regular 2x2 table with male, females on one side, and voted yes or no for a particular issue on the top. And the numbers in parentheses are the totals for the non-missing. But then we also had missing information about some voting information. So these are the numbers in kind of reddish. What we want is to estimate these joint probabilities. Okay, P11 is males who voted yes, P12 is males who voted no, and so forth. And the sum of these probabilities is 1. And it turned out that the likelihood function for this situation can be written as, there are two parts of it. One part is the part from the non-missing, okay, so it's P11, okay, the probability in these cells to the power, because there were 28 cases. P12 will be to the power of 45, and so forth. So that's the end of this one. And then there are 10 people about whom we don't know these individual observations, but probabilities, but we know that the probability was P11 plus P12. So this is the sum here, and it's to the power 10, and then P21 plus P22 to the power 15. And this is the likelihood function. It turns out that in this situation, it's fairly straightforward to solve it analytically, and you get closed form formulas for the probabilities, and you can write them also as a conditional expectations. Oops. What happened? I want to go back. One more.
I went back.
One more.
One more?
To the table.
Yeah.
Okay. Now, I don't remember things from one to the next, so I'm going to skip that. Okay. Oops. Okay. One way to solve this situation is to use a software that is called LEM, that Tor is going to talk about a little later. And LEM is a very powerful freeware. It stands, I always have to look it up, log linear and event history with missing data, okay? So event history is another way to describe failure data, okay? You have events. So it does all of these things. It's not easy to use, but you know, maybe one of these days I'll get comfortable. But the way you specify it, the things that appear after the asterisk are comments, and this is the partial input. So R is the response indicator, S is sex, and V is for vote, and then all the commands are shortened to 3 letters. So MAN is short for manifest, and manifest means it's the observed variables. Okay, otherwise they are. It also deals with unobserved variables type thing, so, and with path diagrams and things like that. So this is just regular variables. We have 2 of them. They are the S and the V. Then there is one response indicator, that's the R. That response indicator has 2 levels. So the first level is for the response variable, the next 2 levels are for the S variable, and the next one is for the V variable. And then the labels of these variables are given here, R, S, V. And then there are 2 subgroups. One is the SV, where we have complete data for both S and V. The next one is just S, where we have complete data just for sex. And then we have the model we want is for the SV part. And the data is entered the way it was there, the 28, 40, 45, 22, 52 is the complete data, and then the 10, 15 is the subgroup S. And then it gives you those conditional probabilities, sometimes called, and these are the estimated probabilities with their standard errors. They are the same as what appeared on the previous slides. And if you only use the complete data, you would get probabilities that are slightly different. The standard errors would be larger because you have less data, right? Okay. And then I'm going to quickly just mention the next thing. Some of you know that I like formulas, I like stata. So there is a matrix language in stata called Meta. I'm actually not very proficient in it, but you can write commands to do it. And I'm not going to go over the command. If some of you want to talk to me later, or you can just look at them. But you can program stata to do that, and I did that. And then if you still remember the output, you get the same output. So it's the estimates of the 4 cell probabilities is on the first square there, and the second square has the standard errors. And I'm going to give it back to Tor.
All right. Thank you, Estie. So that was just a nice little demonstration of maximum likelihood conceptually with a 2x2 table, and shows that you can program an MLE function yourself if you're so inclined. I think, for regression analyses, obviously the formulas would be more complicated. It would be a more challenging undertaking, although certainly it can be done. However, Fortunately for us, there are existing programs that will fit maximum likelihood models for regression analysis, and these appear in two places. One of them is structural equation modeling, SEM programs, and those can fit a wide variety of models for continuous outcomes and mediating variables if that's applicable for your analysis, if you're willing to assume joint multivariate normality. I'll also add that some SEM programs, in particular Stata and M+, also feature robust standard errors for obtaining correct inferences with clustered data. So if you sampled data from some kind of hierarchical structure, like you go to different clinics and you sample participants within clinics or participants within yoga classes or things like that, where maybe the same teacher is giving an intervention to multiple participants, you would want to look into these options for getting the correct standard errors when you have clustered data. But these robust standard errors are also valuable when you are worried about assumption violations of normality or constant variance. So they're multi-purpose standard errors. Some SEM programs also allow for non-continuous mediators and outcomes, and we'll demonstrate a logistic regression analysis with M+, which is one of those programs. Now, the other main place where we see the maximum likelihood method implemented is in mixed models programs for longitudinal data sets where only the dependent variable has missing data. So if you're in a situation where maybe you have a trial and your main predictor is randomization group, then you know what that is, and then you have multiple repeated measurements over time on the outcome, and some of those are missing, a mixed models program may be a very fine way to analyze the data, and maximum likelihood estimation is built in as part of that process. And the appendix lists has a partial list of some of these software programs. So let's look at the first applied regression example. This comes from a tobacco and bars study that was conducted by Pam Ling and her research group up at Parnassus at the CTCRE. They administered a brief survey to 1,217 young adult bar patrons in San Francisco. And if you guys know anything about young adult bar patrons, they're there in the bar, they're having a good time, they may be in various states of intoxication. The last thing they want to do is fill out some kind of long survey. So the design features clustered data from participants who are gathered within these bars using what's called a three-formed survey design with planned missingness. And I'll show you on the next slide what that looks like. For now, the variables available for analysis include the number of days in the past 30 that the participants smoked, and that's the dependent variable. And we have 1,145 of those records. Age in years, 1,217, we have complete data. Race was coded as white, Latino, Black, Asian, Pacific Islander, or other, with the referent group being white. Male gender was coded as a dummy variable. Sexual orientation was gay, straight, bi, or other, with straight as the referent group. There were 1,212 of those records. Then we also asked, does the participant consider themselves to be a smoker? And that's a 0-1 variable, and there's only 858 of those. Then we also asked some questions about how many people in the participants' social network were engaged in smoking. And we have a summated score for that, and there were 616 of those. Then we have an extroversion index, which is a sum of multiple ordinal outgoingness items, and we had 801 of those. So this example demonstrates full information ML, linear regression analysis from a planned missingness design using Stata and also SPSS AMOS. And just to keep things kind of simple, and because AMOS doesn't handle clustered data right now, I just decided to omit variable clustering for venue ID in this example, but we bring it back in the second example, which is a logistic regression using the same data set. Okay, so I promised you guys I would tell you what the three-form design looks like. This is basically what it looks like. John Graham, who I mentioned earlier in connection with the annual review psych chapter, he and his colleagues have come up with this idea for being that will enable you to ask more questions when you're in a time-limited situation. And the basic idea is, if you look at the top row here, top kind of section of this table, you'll see that there are 3 forms on the left side here: survey form X, survey form Y, and survey form Z. And then for all 3 participants are randomly assigned to receive one of these 3 forms. And for all of the participants across all the forms, we have venue ID, we have the dependent variable, number of days smoked, then we have some demographics here: age, race, gender, and sexual orientation. That was measured on, those were all measured on everyone. But if you go to the bottom half of this table, some of these personality variables and social network variables, you'll notice here that this was measured in form X and this was measured in form Z, but it was not measured in form Y. And then if we go over to the social network data, form X participants skipped that. They didn't get it, but they did get the form. They did get this if they were a form Y or form Z participant. And similarly, the extroversion index was only asked the first 2 participant groups, but not the last. And so the idea here is that you can ask more questions by using this planned missingness design, and you utilize the information contained in the pairs of data all together to obtain your estimates and standard errors. And this would be an example of missing completely at random, because whether somebody is missing on the "do you consider yourself to be a smoker" variable, that was randomly assigned by us. It's not due to the fact that it was under the participant's control. And then over here in the very last column, we have another variable that indicates whether they smoked within 30 days of waking, or 30 minutes of waking, and that's a binary yes-no variable, and it can be used as something called an auxiliary variable, and I'll talk about that in a second. Okay, so apologies for what's a little bit of a busy slide, but I'll just walk you guys through it bullet by bullet. So the first thing is, in this particular example, regular old ordinary least squares regression is simply not possible because listwise deletion yields a data set with 0 observations for this model. Now you guys might say, well, that's kind of artificial. You know, how many people are really using planned missingness designs? Well, maybe not a lot, but I want to make the point here that this is really just a more extreme form of the situation that we encounter almost daily when we're trying to fit regression models. And some subset of cases are complete, but a significant number of cases have incomplete data. So the same principles apply. However, this analysis is straightforward if you use the ML method with the SEM command in Stata. SAS has one called ProtCalis. AMOS is available in SPSS, or if you go to a standalone SEM program like ListRoll or EQS or M+. Now, like I said, to keep things simple, I didn't include venue ID as a clustering variable, but you can do it easily in Stata using the VCE cluster, and then you plug in a cluster ID here. And that's just an option that you specify. And in M+, you can do it too, and we demonstrate that in the next example. Now, what about this auxiliary variable business? We don't demonstrate that here to save time, but we could have used this smoking within 30 minutes of waking up variable is what's called an auxiliary variable, and what an auxiliary variable does is it adds additional information to the analysis. It is a variable that is either correlated with observed values for other variables in the analysis, or is correlated or predictive of missingness on those other variables. And I say here strongly, I put strongly, because the technical definition of an auxiliary variable is just a variable that's related to either values, observed values and other variables in the analysis, or missingness on those variables. But there's a simulation study by Collins et al. In 2001 that showed that for auxiliary variables to be beneficial, they have to be pretty strongly correlated. I mean, with missingness on other variables or actual values. And we're talking by strongly, I mean like 0.50, 0.60 or higher. So you don't want to just use auxiliary variables willy-nilly, because if you do, it's just going to add noise to your analysis. So in my experience, when most people are doing ML-based analysis, they just fit their regular statistical model. It's fairly rare to have auxiliary variables. Where you see auxiliary variables used a lot more is multiple imputation, because it's very easy to include them in multiple imputation. It's harder to include them in ML. In the appendix, I give you guys links to Stata and SAS papers that demonstrate how to do it if you want to do it. But like I said, in my typical experience, most people just fit their regular old statistical model. And when they're doing ML, they're not including a lot of auxiliary variables. All right. So I'm going to escape out of here and go into Stata. And I try to make this text big enough to read. Basically, the first thing I'm going to do is just run some preliminaries to tell Stata where to find the data and to log it. And because I made things bigger, it may scroll a little bit. Set more off is something that I would run if I were just running this, if I wanted to run the whole thing all at once and save a log file without looking at the results step by step. But here we want to look at the results step by step, so I'm not going to run that. I will tell it how to load the data though, so that's the first step. And then the first thing I like to do is just summarize the data, because when I do that, it just tells me here, this is like running, what is it in SPSS, like examine or explore, and in SAS it's proc means. But the basic idea here is it's just going to give you the ends per variable. And you can see here, when we start getting down to reporting self as a smoker now, network smoking, extroversion index, we don't have as many cases. So just the humble summarize command can give you some good information. All right. There is a built-in Stata command called mistable that will give you additional information. Well, let's see what it gives us. Mistable actually tells us explicitly how many cases, obs equal dot, that's how many have missing data, obs less than dot, that's how many are complete, and then it also gives us some information about unique values. So that's kind of cool. But let's take it up in even one more step. A sociologist named Scott Long has written a user-written command called misschk, which I'll pronounce mischeck. And if you run mischeck, first of all, it tells you, it gives you a legend here. So variable 1 is venue ID, variable 2 is smoke days, that's the dependent variable, variable 3 is age, and so on. It tells you the number missing. Well, we already had that from Stata. But it tells you the percent missing. And remember, I've been very focused on, do you have more than 5% missing, 10% missing? So this mischeck command is really nice because it can show us, wow, down here, networks, self-reported smoking identification, 30% missing. Network smoking, holy smokes, 49% missing. Okay? Extroversion index, 34% missing. The other thing that's kind of cool about mischeck is that it will tell you the counts for combinations of variables that have missing data. So that's useful for diagnosing potential problems in your data. Like, you know, here variables 2, 4, and 7 are only missing one case, but variables 2, 8, and 9 together are missing 12. So we can go up and we can say, okay, that's smoke days, that's the dependent, and these two guys down here, 8 and 9, well, they're part of our planned missingness pattern, so that makes sense. And you can see down here, 7 is missing 264 by itself, and 8 is missing 444 by itself. And then finally down here, it gives you a count of the number that are missing, like, you know, 1 variable, 2 variables, and 3 variables. So mischeck, it's a useful command. If you're a Stata user, check that one out. All right, so that's all the preliminary stuff. Now, seeing is believing. I'm going to run an OLS regression just to show you what happens. Capture noisily, basically what that does, capture says, allow Stata to keep running even if there's been an error. And I need that for when I run all this stuff en masse to create a log file that we'll post on our website. Noisily says, echo the error. Okay, so when I run this, let's see what happens. There's my Stata output. No observations. There you go. We're stuck. We're dead in the water. But because you're smarter and better looking than your average Stata user, you are now able to run the SEM command. And I'm not going to run this up here. This just basically shows you, if you run it, that at the intersection of those three variables, there's 0 cases. But because you guys are smarter and better looking, you already knew that, so I don't need to run it. Now, the SEM command is what we're going to use to run maximum likelihood estimation for a regression model of smoke days. And this little arrow here symbolizes smoke days regressed onto age. What's this I.race thing? Well, race is a multi-category categorical variable. So it wouldn't make sense if we just put in race by itself. Stata would think it's a continuous variable. We don't want that. We want dummy variables. Now, it turns out if in regular Stata estimation commands you just put I.race, it will create automatically internal dummy variables. Stata calls those factor variables. SEM, for whatever reason, it's a pretty recent command, they did not include factor variable functionality. However, luckily for us, there's an older wrapper command called xi, and what xi does is it creates the dummy variables for us in the data set and then applies them in this model. So when we say I.race, it will create the dummies and exclude the first group, which in this instance happens to be white. Then we have male gender. Then again, I.LGBTcat. Remember, sexual orientation, multi-category predictor. We need to create dummy variables internally, and that's what the I.'s going to do for us here. Then we have self-reported smoking status, network smoking, and extroversion index. Then we close the parenthesis, and we have a comma, which means there's an option coming. And then on the next line, method, MLMV. That stands for maximum likelihood with missing values. Okay, that's the key. That's going to invoke the ML with missing values. So let's run this. And we have some log likelihoods here. And look at this. 1,217, all the available data. As my friend Mike Patetta at SAS would say at this point, let the good times roll. We're really excited because now we have results under the missing at random assumption with our planned missingness design. And we can look here. Age doesn't appear to be significant. None of the race categories, which Stata is abbreviating with an _I, none of them are significant. Male gender, but here, LGBTcat2, which I believe is gay versus straight, that's significant. 3, which is bisexual versus straight, significant. And 4, other versus straight, significant. And then here, look at this. Holy smokes. You ready for the Nobel Prize? If you identify yourself as a smoker, you have more smoking days. Shocking. If people in your network smoke, you have more smoking days. Not a surprising thing. This is interesting. Your outgoingness is not really associated with how many days you smoke. Now, there's a bunch of other stuff down here. In the full information ML method, it turns out that you get a river of additional information because part of the full information ML process is it estimates the means, the variances, and the covariances among the predictors. And that's what all this stuff is here. Ordinarily, you would not bother to interpret that. Okay, now, we're not done, right? Because often we want to know, is there an overall effect for race? Is there an overall effect for sexual orientation, right? So to do that, we can use several different Stata commands. There's one called test, and there's one called test parm. And they're similar, but there are a few differences. And Estie, I don't know if you want to say what those differences are?
Sure. Test parm is really shorthand, and if it works, you don't have to specify as many variables. You can use the asterisk as a short thing. But you see, they're absolutely identical. The output from them looks absolutely identical. If you do help test or help test parm, you'll get both of them. And there are 4 different syntaxes, and they get more complicated when you have multiple equations. which we don't have here.
Yeah, so we just show them to you. Thank you, but yeah, but I mean here you get the same answer for
Smoke days is the name of the equation. The thing
right.
is square parentheses.
But there is an omnibus difference here for LGBT status. Okay, so there's an overall difference between the sexual orientation groups, and this is that's all the single equation, and then you can have a multiple equation example down here, which you would want to use if you were using auxiliary variables and incorporating them into the analysis. But for most typical applications, you wouldn't need that level of specificity. Okay, so now let me head back to PowerPoint and just summarize the results here. So the results are based on maximum likelihood, also known as FIML, when the dependent variable is continuous and normally distributed. There are no significant effects for age, race, male gender, and extroversion, but there is an overall effect for LGBT status, with gay participants having the lower mean number of smoking days relative to straight, and bisexual and other having more numbers of smoking days. And that's kind of an anomalous finding for the gay participants, because we know from the literature that there is LGBT folks tend to smoke more, which is one of the reasons why these data were collected. So that would make us want to check this model more, maybe think about how is the dependent variable being conceptualized, like do we need to log transform it because it's a count? Do we want to maybe go to a negative binomial regression instead? So that's just something to be cautious about. Not surprisingly, self-identification as a smoker is positively associated with the number of days smoking, and so is having folks in your social network who are doing smoking. All right, we're a medical campus. We do a lot of linear regression, but we sure do a lot of logistic regression too. So if we go back to this data set, what if we want to know what the association of these previously studied independent variables were with whether someone smokes every day, which is a yes or no variable? We probably want to use regular logistic regression. We'd use a general purpose logistic regression program to do that. But if we try and do that with this data, we're going to get 0 observations. If you were doing it with one of your data sets where there was a significant degree of missingness, you would probably lose a lot of data. Now we can use maximum likelihood estimation, and we're going to do it in M+, and this time we're going to include venue ID as a clustering variable to account for this sampling of participants within bars. The reason why I'm using M+, which is a standalone SEM program, to do this is because none of the general purpose programs do this. And the reason why they don't is because unlike the linear regression situation, there's no closed form solution for the likelihood, so we have to simulate it. And M+ is a very specialized modeling program that if you have a lot of missing data, you're fitting models all the time with logistic regression and Cox regression. M+ is probably a good program to have in your toolkit. Now, in this demonstration, I'm going to call M+ from Stata. The reason why I do that is because it's kind of cool to show you guys who use Stata how to do this if it's possible. It also makes your M+ outputs more manageable because you can stack multiple model runs and save them to the same log file, so you avoid a proliferation of endless M+ outputs. But I really want to emphasize that if you're not a Stata user and you want to use M+, you can just do all this stuff directly in M+. You don't have to have Stata to do this part of it.
You can do the same thing in SAS too.
If you're highly motivated.
Well, I'm having to deal with those 1,000 individual files.
Right.
Is highly motivating.
All right. So let me go back now to Stata. And here it is. So the first thing I'm going to do is have Stata generate quietly some dummy variables. So it turns out if you run the tab command and generate a frequency table, Stata can also create dummy variables for you. And that's because M+, for all its sophistication, does not create factor variables or dummy variables for you. You have to input them manually yourself. And that's what's done here. So we feed all the variables for the analysis into run M+, which is the Stata wrapper command. And you can see here now we have dummy variables for the 4 race ethnicity categories, and we have dummy variables for the 3 sexual orientation categories. And then we tell it cluster equals venue ID. Analysis type equals complex. That tells M plus that we have clustered data. We're going to use the maximum likelihood with robust standard errors. That's what MLR stands for. Then down here, remember I said we have to simulate the likelihood. So that's what these two statements do. If you have multi-cores in your computer, I highly recommend the processors command. That'll help speed things up. Then here, categorical, smoke daily. That tells M plus that the dependent variable smoke daily is binary. Okay? Then the model statement, I have a bunch of repeating lines here that regress smoke day onto first race 2, then race 3, then race 4. And the reason why I broke them out into separate lines is because I want to have these parameter names, R2, R3, R4. That's because down below here, I'm going to set up a multi-degree of freedom omnibus test for the race effect, kind of like what we did in Stata previously, where we tested the overall effect of race. Now, you'll notice here there's a bunch of rows that simply say age, race 2, race 3, race 4. What the heck is that? Well, what we're doing here is we're bringing those independent variables into the model as continuous random variables that will inform the maximum likelihood estimation. And then finally, down below here, I have output confidence intervals. That's what C interval stands for. So I'm going to run this block of code, and...
Better with the tab now?
Did
you run the tab?
Yeah. We would have gotten an error otherwise.
I know.
Okay, so this is a DOS window that M plus kicks up while it's doing its estimation, but you see that wasn't too bad. Okay, here's the output. So M plus, the first thing it does is it echoes back to the stream the input commands that you gave it. And then we always like to see this message, input reading terminated normally. And then it gives us a summary of the analysis, tells us 1,217 cases, only one group, one dependent variable, 12 independent variables, and then it summarizes those variables down here. There's a binary or ordered categorical variable as the outcome, that's smoke daily, and then you have all these independent variables here which are familiar. Venue ID down below here, that's the clustering variable. A lot of details about the estimation, which for the sake of time and avoidance of tedium I will bypass. Then it shows you the covariance coverage of the data. That's the amount in common for all pairs of variables. How many observed cases do we have for each pair? And you can see as we get down here to network smoking and extroversion index, there's only 23% of the cases have observed data for both of those variables.
The diagonals are not all one.
Yeah, I don't know. Maybe that's the univariate coverage. I'm not sure. All right. This is what we really want to see. The model estimation terminated normally. And then we get the log likelihood and a few information fit statistics, but then the heart of the results down here. Here you go. Now these are the regression coefficients on the log odds scale, and you can see race 2 is significant, so is race 5, and LGB3 and 4 sort of marginally, and then again, consistent with what we saw before, self-identification of a smoker strongly associated with daily smoking. People in your network smoking also associated, and now extroversion index. Extroversion index is positively associated with daily smoking. Now, often in logistic regression, we'd prefer to interpret odds ratios. Well, M plus gives us those, and they're down here. So you can see for race 2, there's about a 30% lower odds if you're in race 2, which I believe is African American or black, of being a daily smoker. And similarly here, if you look, if you're a self-reported smoker, your odds of being a daily smoker are 21 times those if you're not a daily smoker. And so on for people in your network smoking and extroversion. And then down below here are the 95%. Well, these guys the 5%, that's the 90th percentile confidence interval. The 2.5%, that's your 95% confidence interval, and your 0.5, that's your 99% confidence interval. And that's basically it. Now, I did say before, we wanted to know, was there an overall effect of race? And that is shown here in the Wald test for parameter constraints. You see 4 degrees of freedom, that there were 4 dummy variables that we tested for race. And indeed, here are the p-values less than 0.05. So if we're following that significance convention, race, we would say there's an overall difference for race. Now, one of the oddities of M+ is you cannot do multiple Wald tests in the same run. So we're going to refit this model exactly the same as before, but the difference here now is instead of testing the R parameters, the race parameters, we're going to test the S parameters, the sexual orientation parameters. So I'm going to go ahead and run this, and it's going to do exactly what it did before. But we're going to look at the Wald test in the output to see if there's an overall effect for sexual orientation. All right. Here we go. I'm just going to scroll down. Yep, there it is. 15.68, 3 degrees of freedom, statistically significant. So that's how to do a logistic regression using direct maximum likelihood estimation in M+, called through Stata. Now, I promised you guys I'd show you SPSS AMOS. I forgot to do that, so I'm going to circle back. For those of you who are SPSS users, for the linear regression, here you draw the model. And you'll notice here that there are rectangles for all the independent variables, and then over here on the right side is the dependent variable. And I've labeled with parameter constraints R2, R3, R4, R5, L2, L3, and L4. Those are for doing multiple degree of freedom tests of the race and sexual orientation effects. And to do those tests, we set up nested models in the Manage Models window where we set R2 equal to R3 equal to R4 equal to R5 equal to 0 for race, and then we do something similar here for LGBT. We set all those effects equal to 0, which would mean those dummy effects are jointly not significant. And then to run it, I just click the little abacus. It runs. I'm going to load the output, and I'm going to look at the estimates, and here are my regression weights, standard errors, the CR, that's the Z statistic, same as we saw in Stata. Numbers look very similar. And then down below here in model comparisons, assuming that the default model, which was our starting model, was correct, race 5.72, a P of 0.22, LGBT 3 degrees of freedom, chi-square of 21.43, and the p-value is less than 0.001. So this is just a quick tour of how you can do this if you're an SPSS user. All right, I know we're approaching time here. I have one more example, if you guys can hang with me. I'm not going to summarize the results in the interest of time, but I did want to talk about this third example because it's a pretty exciting one. Larissa Duncan, who some of you may know, and some folks down at CAPS, and Rick ran a study to see whether, a pilot, to see whether a mindfulness-based stress reduction intervention would reduce symptoms experienced and bother distress from taking antiretroviral HIV medications. And that paper was published in the Journal of Pain and Symptom Management back in 2012. The study involved 76 people who are living with HIV who are actively taking antiretroviral therapy and who reported distress from ART-related side effects, and they were randomly assigned to either the MBSR program or a waitlist control. Study retention was solid, with 86% completing 3-month follow-up and 71 participants completing assessments at 6 months. So this is a situation where we had some people drop out and then come back in. So we couldn't use our weighted GEE, at least not in SAS. The primary independent variable is randomization group status, and the dependent variables, there's two of them. We looked at the sum of the number of symptoms they reported, and because that was a count, we log transformed it. And then also the average bother that they attributed to those symptoms. And in this particular analysis, we used what's called a doubly multivariate repeated measures design because we had these two correlated dependent variables. But I want to emphasize that the principles that I'm about to demonstrate can be applied to the more common case where you have just one dependent variable for the analysis. And what I'm going to do is show you in SAS that you can fit it using a traditional ANOVA. It's going to drop a bunch of cases. And then I'll show you how to fit it in the mixed models framework with maximum likelihood estimation that will use all the cases. And you will see the results are different. All right, so first thing I'm going to do is tell SAS where to find the data. Then I'm going to run proc-MI, and you guys are wondering, well, what the heck is proc-MI for? That's for multiple imputation. You're doing that 2 weeks from now. Well, that's just a nice SAS tool in this context to show what the patterns of missing data look like. And you can see here randomization status we know for everyone, and then the baseline log of the number of symptoms and the average bother. Those are all observed. But we have 9 cases on this third row where they drop out at the second measurement but then come back in. And then we have 2 cases that are just lost after baseline. All right, so if I run kind of your classic grandfather's analysis of variance, there are multiple ways you can look at this. I am going to look at what are called the univariate statistics, and there's kind of maybe a hint of something for randomization status. But the first thing I'm going to do is go down here and look and first and see if there's a three-way interaction between the measurement, the time at which the measurement was taken, and randomization group. Because if there's a three-way interaction, then I need to decompose that interaction. But luckily for me, it's not significant. But what I really care about is time by randomization status. I want to know, does the result for these 2 measures change as a function of what group you're in and what the time of measurement is, right? Because I want my post-intervention measurements to show a difference between the 2 groups. And this is suggesting no, there's really not a difference. All right, so you guys would say, well, that's kind of an old school way of doing this. You know, a modern way would be to transform the data so that instead of having 1 row per subject and 6 measures, I'm now going to have 6 rows of data per subject and just 1 column representing the dependent variable. And that's what this code does.